All right. So let's start today by taking attendance real quick so we know what the scoop is. Haley.
Here.
Cole. Cole is connecting to audio, I think. Zach is there. We can't hear you, but I do think you're there. Savannah?
Here.
Eliza?
Did you hear me?
Yes, I got you, Savannah.
I'm here.
Bree?
Here.
Grace? Grace is not here. Greg D?
Here. Power went back on. I submitted the quiz.
Wow, that was very quick. Thank you, Greg.
Yeah.
I'm glad it's back for you because that's a pain. Emily.
Here.
Olympia. Seeing Olympia. Jenna. I think Jenna's going to be out today, actually. Daniel. I think Daniel's there, right? You just no audio.
I'm here.
Oh, you're here. Okay,
It
great.
takes a while to unmute. I don't know why. It's like a 10-second delay whenever I click the button.
Oh, that's annoying. Yeah. Greg M. Oh, keys. Ashley.
Here.
Kyle.
Hello.
Here. Saga. Ada.
I'm here.
Elizabeth.
Yep.
And Mary Pat.
Also, Professor, with the first quiz, I thought I submitted it in the PDF file. Can you not open it?
Yeah, so I am running into this problem with several of you. If I've emailed you and asked you to change or send it again in a different format, it's because I can't open it. And occasionally it'll get wonky and, you know, you might be, let's see here.
Also, sorry to sidetrack you, but in the group chat, 3 people have said that they're here and they missed.
Oh, thank you. Okay, Grace, thank you. Cole, I think I've seen the bot and your mic didn't connect, Mary Pat. Whoop. Okay, this is pleasant. Anybody else have trouble with AirPods sticking in your ear? They don't want to stay in my ear. Elizabeth, yes, I see that you had it in a dot pages. And then you do also have a PDF that was submitted later, and now I can see that. So I'll make sure to change that grade.
So both of those you can see then, and that's working okay?
For quiz 1, yes. But
for quiz 1, okay.
But so several of you I've sent messages to about the exam. That was the main concern I had because I want to make sure I can grade your exam. So if you received a message from me saying that you need to re-upload, make sure you have an opportunity to do that. It's mostly just getting your exam either in a PDF format, or if you want to just email it to me directly instead of submitting it, that works too. But sadly, with Pages, it won't even open on my computer because I have a lame PC. So it doesn't play nicely.
Both of those parts for the quiz 1 is okay, or should I email you?
No, quiz 1 you did just fine. I think the issue I had with yours, Elizabeth, was the exam.
Or no, I meant the exam, yeah.
Yeah, the exam I only got a dot pages document. There's no PDF.
Can I email you?
Yep, if it's a PDF, definitely. That's
Okay.
not a problem. Yeah, and there are several others that I emailed out to. So please check your emails. I just want to make sure that we can get your grades in, right? Like that's important. It's important to know how you guys are doing. And several of you use Max, which is totally fine, but I want to make sure that I can see your work and can actually grade it out. Okay? All right. For today, we are going to be talking about hypothesis testing. So let's get that put together here. On our class website, you should be able to see all the assignments coming up. We are next week going to be having just more practice. Let me actually, I think this might be worthwhile to pull up our syllabus, make sure everybody is on the same page. Here we go. All right. So this is where we are today. We're going to do hypothesis testing, which will be t-test. That's what we'll really be doing. We had the quiz and then lab 4 is today. Next week, we're going to be practicing lab 5. And the week after that, lab 5 will be due. And there will also be a quiz. So quiz 4 here on November 11th is going to cover what we discuss in class today and what we talk about next week. Is there a question? Nope. Okay.
You said lab 4 was due? Okay.
Yes, so last week we practiced the lab.
For lab 3, it still says that
Oh, it's
you
lab
can't.
3 maybe instead of lab 4. Sorry about that if the numbers are wrong.
Oh no, that's right. I was just saying lab 3 still can't be submitted until tomorrow. But I thought it was supposed to be due
Yeah, I thought it was supposed to
today.
be done too.
Wait, I thought I literally just fixed it. It's still
Like-
not fixed?
Now, I just checked it after the exam or the quiz and it was not.
Yeah. So oh my gosh. Oh wait, I'm confused.
You should just be able to like submit it anytime.
Yeah, have
It's
you guys
still-
tried refreshing your page? Because I did that and then it started working again.
Okay, it's there. Yeah, it's there now. It wasn't there like right after my quiz, but
Yeah.
it's there now.
Sorry, you guys. This is, I
No,
Is there any way we could? Okay.
don't have a good answer. Now, a handful of you did email me your submission. That's totally fine. That works too. You can always email me, but know that if there's something wonky, okay, well, just blanket statement. I am not doing late work docking of points. I'm not doing that. So if you guys are panicking and you're like, oh, I'm supposed to have something submitted and I can't submit it, there is no way that I would ever penalize any of you for a technology error. That just seems absurdly wrong to me on an ethical, moral level. So let's have that understanding as an umbrella to start with. Second of all, I'm just not a super like anal professor who's like, well, it was, 3 minutes late. No, I have to follow a lot of the guidelines that our university and department follow. So that's why there's a lot of this language in my syllabus. But I think by now, maybe if you've recognized, I'm kind of chill. I want you guys to succeed, and whatever way that I can come alongside you and help you succeed, that's what I want to do. So with that said, if there's ever something wrong, please do reach out. And there's several of you, there was, maybe this was my research class, like somehow one of my lectures hadn't uploaded correctly, there was an error. Definitely let me know. I'm making mistakes, I'm human. This is all brand new, doing everything online this way. So again, semester of grace. So I hope that alleviates some stress for you guys. If ever there's errors like that, know that you are not going to be penalized for it. Does that help, Elizabeth? Okay.
Yeah, I had just looked at it for this week and I was like, yeah.
And I had another student reach out and they were
Yeah.
like, life is bananas. I don't have a chance to finish the lab. Totally fine. Let's work at it together. As long as I know, and I'm not wondering if you're like, dead in a ditch with COVID because I haven't heard from you, right? Like, I just want to be able to help out. So if you let me know, we will figure it out. Sound good?
Sounds
Yes.
perfect.
Thank you.
Okay. All right. And then I just want to reiterate the final project for this course. There will be really no lecturing or anything like that after Thanksgiving. There's going to be the exam, and then there's going to be a final project. Now, my weeks here, I need to double check if there's one more week after that. There may actually be one more week. I think finals week is technically the 7th through the 11th. At which point we are going to split those up. We'll have the exam on one day and the final project. I think I talked to you guys about that. The final project, I'm going to give you guys ahead of time. You can work on it. It's usually something that we did in class, but I'm going to give you guys a couple weeks to work on it on your own. And then it's nothing that you need to gather data or anything like that. And there's no extensive workup, like write-up that you need to do. It'll be doing some stats using Excel and then describing your results. Like, what does it mean? Kind of like what we've done in the labs. So I just want to alleviate any fears about that. Like, it's not like you were supposed to pick a topic and write a paper. Like, that's not that kind of final project. It's really integrating everything we've learned in the class and how to interpret and analyze data. Any questions about that?
No, that sounds perfect.
Okay, now I also want to clarify, exam 2 is not cumulative. It will only cover the material that we lectured on after exam 1 up until the end of the course. Now, having said that, like for instance, we learned how to do a mean earlier this semester. You may need to know how to do a mean to do some of the other calculations, but I'm not gonna go back and ask you about z-scores, for instance. That's not what this is gonna be about. Make sense?
Yep.
Questions from anyone? Going once? Going twice? I'm gonna let a whining puppy in. This is the life now. All right, and so today the whole point is discussing how we test out our hypothesis if we have 2 different groups and we want to know if those 2 groups are the same or if they are different. By the way, say hello to Oakley, who's turning into a giant already. Say hello, class. Oakley, the golden retriever puppy. Okay.
He's adorable.
Thank you. I think so too, but I'm a little biased. All right, so let's get this put together here. Here's our hypothesis testing. I want to make sure we can get that shared. Zoom never likes me. It never wants to actually open what I want to open. Here it is. Okay. So hypothesis testing. Do you guys, is that a concept or a term you guys have heard before? Test your hypothesis?
I mean, I haven't heard it as like a bolded word in a book, but it kind of seems like a natural progression of trial and error.
Mm-hmm. Any other thoughts? Anybody else kind of go, oh yeah, that's kind of familiar. You got to participate a little bit, kiddos.
Yeah.
Can't have thank you.
Familiar. Totally familiar.
Okay. All right. So this is something like if you think about, I have a curiosity, I'm wondering about X. You might get to, in your mind, you might go, well, what's the reason why they might behave this way? And then you create some ideas or some possibilities or some hypotheses as to why something may be the way that it is. But those will continue to remain hypotheses and could possibly turn into assumptions, right? Some idea or even a feeling on how you think something is. But unless you test it out and know for sure that that is actually what's going on, that's the bad science, right? So if I'm curious to see if there's a difference between men and women and the way that they interact with social media, and in my mind, I have a couple of hypotheses. I'm thinking, well, I bet you that women use it more because they're chattier and they need more social connectedness. And I bet you that males, when they do use it, just use a couple of different words, right? Just, yeah, no, I'm making stuff up here. So that's my hypothesis. And I'm positing in there that there's going to be a difference between men and women. If I decide that that's just what it is, and I'm not going to test it out, that's making an assumption, right? If I decide, yep, that is what it is, That's bad science. I need to actually test it and see if my hypothesis is correct. See if the data that I gather supports my idea on gender differences between men and women. Now, we need to also talk about and think through, like, does any difference matter, or does it need to be a certain amount of difference, right? So if I say that women use it more, and on average they log on to social media 10 times per day, but men log on to it 9 times per day, that's different, right? But is that different enough to be significant? Could that just be random error from one day? So those are the things we need to keep in mind when we're thinking about comparing groups, we're coming up with hypotheses. We need to think about and how we're going to shape it to understand like the differences that occur and whether there's significant differences or if it's just standard error, right? On any given day, somebody could use it more, somebody could use it less. All right, so this is one of those ideas, like in terms of hypothesis. So there's in your text, the example that's used is stated by an economist that states people may not remember too many numbers about the economy, but there are certain signposts they do pay attention to. As a short, hard way to assess how the economy is doing, everybody notices the price of gas. So let's have a little chat about that. Do you guys think about that? Like, how much does gas cost? Do you have a memory of when gas was either really, really expensive or really cheap?
2008, gas was expensive.
It was really cheap this summer.
Yes.
What is the cheapest you guys can remember paying for gas?
A junior year, which was in like 2017, gas was $1.70. That was in Illinois.
Okay. So cheap or expensive?
Cheap.
Because when you say that, Daniel, to me that seems cheap, right?
Yep.
Yeah.
In the UP, that's just expensive every time. That's like always in the $3.
Okay. So geographic awareness, right? Okay. What's the most expensive you guys have seen price of gas?
$4 and up.
Okay.
$4.27.
Yeah. So I have this memory back in California where we paid close to $5 when we lived out there for gas. But I conversely also, I want to say it was in the early 2000s, we paid like less. There was a date, it was less than $1. So it hovered around $1, then dipped below $1. So anyway, so that's often a marker for how people feel. How's the economy doing? How are we doing? Right. It's one indicator, right? But it ties to people's memory, and that's often something that's used. If you think of your grandparents, there are a few things about cost that will get brought up. Gas is one of them. Cost of bread or milk is often something that's brought up, or even a cup of coffee, right? Because they're like, wow, in my day, we didn't spend no $6 on Starbucks drink. It was 55 cents at the local diner or whatever, right? So those are markers that we utilize. But from that, we create hypotheses, right? The price of gas has only gone up in the last 20 years. Somebody might say that. Or the cost of coffee has grown exponentially over the years. So we can use kind of these comparison statements based on a particular hypothesis. But then we need to use data, right, to figure that out. So there's additional information here on random stuff about gas, which I don't think is necessarily relevant to our class, but it gives you the idea that we create hypotheses all the time about the silliest of things, right? It's not just when you're sitting down and thinking about a research project. We go through this every single day to go, why is this like that? I believe it's like this because of insert the hypothesis. So in terms of the price of gas, this is one of the studies they talked about. So in May 2016, random samples of California gas stations showed that the average price was $2.73. The national average at that time was $2.32, okay? So here we have a sample, right? The sample is 100 gas station in California. I would want to know where in California because that'll impact it too, but anyway, neither here nor there. And then the national average at that same time was $2.32. So from that, we have two options. It could be that the average price of gas in California is higher than the national average, or the average price of gas in California is really the same, and that specific sample just happens to be particularly high. And that points to standard error. That goes back to my example a minute ago when I talked about social media engagement and interaction. You know, if there's a difference, could it just be, you know, random error of that day or sample error? That's not really indicative of a societal trend or occurrence, right? So in order to determine which of these two scenarios is more likely, is it in fact that in general, California is more expensive than the national average, or is it that they're about the same, but that in that particular sample, that was standard error? So what we do to answer that is we use statistical hypothesis testing. And the way we end up doing that is by comparing and assessing our hypothesis. So what a statistical hypothesis testing is, what is it? You know, what's the definition? It's a procedure that allows us to evaluate hypotheses about population parameters based on sample statistics. So we've talked about that quite a bit this semester, right? A sample statistic is something that we can measure. It's more easily accessible, takes less time, it's more efficient. And it allows us to generalize or give us information about the general population and gives us a hint as to a population parameter. So the hypothesis then becomes the average price of gas in California is higher than the national or the average national price of gas. That is the hypothesis. So few things that we have to know or assume before we move forward. We have to assume that the sample was randomly selected, right? If you find a gas station and there's 4 of them at each corner and you're right by a highway, that might be a little cheaper than if you're in little podunk town that has the one gas station that everyone has to use, right? There's the way less supply, more demand. So we're gonna assume it's a random sample and that the variable is measured at the interval ratio level, right? We're getting an actual measurement of price. It's not categorical or anything like that. We cannot assume that the population is normally distributed, right? We cannot assume it's a normal distribution because across the country, there may be some variability. What was that? I thought I heard somebody ask a question. No? Okay. And because our sample size is sufficiently large, it's greater than 50, we know that based on the central limit theorem that the sampling distribution of the mean will approximate a normal distribution. Okay, those are our assumptions. Is anybody else hearing somebody talking or is it just me?
No, I hear it.
Him a new toy.
Can somebody mute themselves if we're having a side chat? Okay, thanks guys. All right. So again, the research hypothesis is a statement that reflects a substantive hypothesis or a statement about the population. It is always expressed in terms of the population parameter, but can be specific from test to test, okay? Now, in our specific research hypothesis, the H1 also presented as, you know, the alternate hypothesis. We state that the average price of gas in California is higher than the price of the gas at the national level. So we use mu, right? Because that's the population mean. So here's what it would look like. So your hypothesis, H1, is that the mean of gas is greater than $2.32, okay? So the average price of gas in California is higher than the average price of gas nationally, okay? So that is, and because we're approximating a population parameter, we use that same language. We use the nomenclature for a parameter. So that's why we use a mu rather than an X bar, right? Okay. So here's the different ways you are going to see hypotheses when you are comparing two groups. You are going to see it either as it's not equal to some specified value. So it'll be mu does not equal whatever. It'll be greater than or smaller than, okay? So that is going to be a directional hypothesis where my hypothesis states that it's going to be higher or less than, right? I'm predicting that if I'm on a normal curve, let me draw it out here. If I am on a normal, whoops. Sorry about that. Okay, so if I'm on a normal curve, okay, there it is, right? This looks familiar. And I'm saying this is 2.32, that's the price of gas. My hypothesis would be that it would be higher than that. So I'm testing this tail. We're going to talk about that in a minute. I'm not testing the entire normal curve because it's a directional hypothesis. I'm saying it's going to be higher than that. If I said it will not equal, which would be something like this. If I was saying it's not, mu does not equal 0, okay? I'm saying it's not going to be this value, then it's going to be really bidirectional. It could be either tails. It could be higher, it could be less than, but I don't know. So there's going to be some hypothesis you guys are going to see, or some research instances where you're not necessarily going to know one way or the other which way it's going to go. You're just, your hypothesis, it's going to be different. That's what it's going to be.
Not to slow your roll down.
Yeah.
Mary Pat is having trouble seeing you.
Oh, no.
She asked, is your camera?
Yeah. So you'll notice, Mary Pat, I have two, because my AirPods won't connect to my laptop, I have two boxes with my name on it. So you got to find the one that's got my face on it. But the good news, does that help?
Yeah, okay. Thank you.
Sorry about that. And know that also this is being recorded, so it'll be on our YouTube channel as well, so you can watch it. I'm sure you guys all love to do that. Watch it next day.
Absolutely.
Yeah, puts you right to sleep talking about hypothesis testing. All right, so that's something else to be mindful of, that hypotheses can be directional or non-directional. Whoops, and now this won't click. There we go. All right, so let's talk for a minute about the null hypothesis, because all along we were talking about the alternate. You probably heard me say that. So H1 or HA is the alternate hypothesis. The null hypothesis is a statement of no difference. So it contradicts the research hypothesis. So for instance, earlier in our example of gas, where we said the gas in California is higher than the national average, that's our alternate or research hypothesis. The null hypothesis would be the price of gas in California is the same as the price at the national average, or there is no difference in the price of gas between California and the national average. Okay, so the null hypothesis says, nope, there's no difference, they coexist and it's the same thing. Okay, so at times it can be that the null hypothesis has a specific value, right? It could be a number, but it's often possible too that it's just going to be a no difference piece. So I kind of just explained all of that. Under the null hypothesis, for instance, observed differences of 0.46 can actually be due to the fact that our sample happened to contain California gas stations with higher prices, like I was talking about, because I'm just going to go back real quick here. Here it is. 273 was the price in California. 232 is the national average. If you do the difference between that, right? Okay. So it could be that the difference in price is just random, right? It could be due to sampling error, like we talked about. But since statistical inference is based on the probability theory, it's impossible to prove or disprove a research hypothesis directly. So we only estimate how likely it is to be true and how likely it is to be false, which is why we have to set up a hypothesis that counters our research hypothesis. And that, again, is called the null hypothesis. When we do a study and we gather data, we will either reject the null hypothesis, therefore accepting the research hypothesis, or we will fail to reject the null hypothesis, at which point we are saying, in fact, there is no difference. We could not reject the null hypothesis, therefore it must be the same. We never say it proves, right? We've talked about that. That's not language we use. We never say that it's confirmed. We use the words we reject or fail to reject. So you should be writing a big note somewhere in there, an asterisk if you're typing, bold it, do something. That is the language you will always see in any research paper and in anything you guys are writing. That's the language you have when you're doing hypothesis testing. So if your hypothesis is, we think men are going to be using social media less than women, the null hypothesis is that there's no difference between men and women in their social media use. You get data, you would either reject the null hypothesis that they use them the same, or you would fail to reject the null hypothesis, which would mean then that your alternate hypothesis was correct or was supported. Questions about that? We on the same page here? Does that make sense?
Mm-hmm.
Okay, you said never say confirm, and what was the other word you don't use?
Prove.
Prove. Thank you.
Yeah, so nothing in statistics really goes to causation or and prove. That's not the language we would use. We would say instead reject or fail to reject. Mm-hmm. All right, so I kind of alluded to this already. You will have one-tailed tests and two-tailed tests. In one-tailed test, that's when you have directionality. So that's a hypothesis test in which the alternative is stated in such a way that the probability of making a type 1 error is entirely in one-tailed. Now, there's a lot of language here you guys don't know about. We will dive into type 1 and type 2 errors in just a minute. But know that in a one-tailed test, it's a directional research hypothesis. So it specifies the value of one group as being greater than or less than a population value. So again, you're just looking at one side of your normal curve. So that's one-tailed. Diving in a little bit more, you can have a right-tailed test or a left-tailed test, okay? A right-tailed test is a one-tailed test in which the sample outcome is hypothesized to be to the right tail of the sampling distribution, right? So that means it would be greater than a specific value. So in our gas example, the price of gas in California is greater than the national average. We're looking just at the right side of the tail, right? When I was doing this terrible little drawing here, that's just looking at the right side. A left tail test is, again, a one-tailed test, but where you're really just looking at the left side of the tail. And it's usually that you're seeing less than a specific value, okay? So I am gonna estimate the height of, average height of men in Idaho compared to Grand Rapids. I'm making stuff up here. That men in Idaho are shorter than the men of Michigan. Okay. These tests, specifically the one-tailed tests, are less stringent or strict than two-tailed tests because they tend to be more conservative. Now, how do we know this? Let's compare that, right? If I'm looking at just one side, all of the error is found in that one section, right? So if I'm doing a confidence interval, what's the common confidence interval? What's the common number we're looking at that we want to be confident at? I'm not phrasing, 95. Is my question?
Yeah,
95.
Okay.
Yeah, I was not phrasing my question correctly, but you guys are right on, 95.
It's the Z-score because it's 1.96.
1.96. Check, right. Okay, so then if you think about that, now I've got a one-tailed test. That means if I'm just looking in this section right here, there's 5% of standard error, right? Well, that 5% is all going to be on this side, right? So that's different than a two-tailed test where my standard error is then split between both sides. So instead of having 5% here, it would turn into 2.5% on either side. So it's it's harder, right? Like you're going to be more strict, more stringent with that. All right, so let's talk about two-tailed test. That's where you're going to be rejecting, the region for rejection is equally within both tails of the sampling distribution. I just kind of described that. So because of that, that's more stringent because it reduces the standard error that's possible. Again, there may be some theoretical reason why we say that they're going to be different, but maybe there's not enough data to make a prediction one way or the other as to whether one is going to be higher or smaller or less than a specific population group. Another reason why you can also use two-tailed test is that you can often get opposite results of what you predicted. So if you use a one-tailed test, even if you have significance, the results could be inconclusive. But if you say you're not sure which way it's going to go, you may get better data that comes out of it. Now, I talk about SPSS in here. We're not going to be, obviously, not using that this semester, but you can do a t-test that's one-tailed or two-tailed in Excel, and we're going to talk about that next week. All right, so let's see what that looks like. So again, if we're using an alpha level of 0.05, that's saying we're allowing 5% of error, or we're 95% confident. This is what the one-tailed test would look like, right? You can see the shaded area represents each side of the tail. And this is a two-tailed test. So again, that's where your error falls, okay? Now, probability values, because that's what we do, right? We're gonna create a specific analysis, and then we're gonna look at the probability value. So when we are assuming that our null hypothesis is true, we want to determine whether our sample evidence casts doubt on that assumption. So again, our null hypothesis is that the mean is $2.32, right? That even in California, that's what it's going to be. But our research hypothesis says that it is higher. The mean in California is higher than $2.32. So we can compute a z-score so that we can figure out the difference between a population and a sample. And that's something that we know how to do quite well now. And then we'll find a p-value, which is the probability that is associated with that value of z. We can also look in this semester, actually, the semester we'll use all of those. We'll use t-tests. F-tests are going to be for chi-square, and R scores, those are for correlation. So any test where you are inferring about the population, we will use a p-value or a probability value. Now, p-value, we talked about this before. You set your alpha ahead of time, and you'll say that you're looking for a significance at the 0.05 level. So if the probability is less than 0.05, then we know that the results you got are either well, what's the language that we use instead of me just feeding it to you? What does it say about our null hypothesis? If you have a probability that is less than 0.05, you can therefore reject the null hypothesis, right? You reject it because the research hypothesis steps in. If it's greater than 0.05, we fail to reject the null hypothesis. We don't have enough evidence to reject it. So we don't know, okay? All right, am I losing folks here, or how are you feeling about that?
Okay, so question. On, like, going back to the gas prices.
Yes.
So external factors, like, say there was like an earthquake. I know.
Yep.
But like that would jump gas prices. So would that be leaning towards more of the null? Like, oh, we failed to reject it because, like, California, we don't know that they typically have higher gas prices because they just had an earthquake, and this is more of a time of limbo, so we don't really we can't say positively.
Yeah.
So that's failed to reject?
Well, I would hesitate to go down that path, and here's why. When we are doing these research questions, right, well, two things. So one is when you're setting up a specific research, oftentimes you want to pick a time that's a weird time to see if there's a difference, right? This is no longer normal. I want to see if there's an impact because of X catalyst, right?
Oh.
And then you want to look specifically at that. But for the purpose of this class, that's my number two then, the purpose of this class, we're never going to look at what I would consider the fringe or confounding variables that may find them. So that's just beyond, that's going to be something we cover in research methods, and we talk about that a little bit more on how to really evaluate the meaning of the data you get. For this class, it's just going to be about understanding the numbers. So if this is my mean, right? I've got a mean of $2.73 among 100 gas station. I'm going to assume that it's, randomly selected. I'm going to assume that it's like normal condition. And I know that at the same time, the national average is 232. So we're just presenting the numbers and then seeing what comes out of it.
Okay.
Does that kind of make sense?
No, yes.
Okay, it's a good question.
I
Go
just
ahead.
want to make sure that we're, sorry if I'm a couple steps behind, but
That's okay.
we're either rejecting it, but we're not confirming it. We're either rejecting it or we cannot reject it.
We fail to reject it.
Okay.
Which is like weird language. Like no one wants to be like, I failed. But that's the language that we use in statistics. You fail to
That
reject
makes
it.
sense.
Yeah. Okay. All right. So here we are at that p-value. Okay. So z-test, right? We know this like the back of our hand by now. So let's assume that the null hypothesis is true, and then see if our sample evidence, right, if our research hypothesis casts doubts on that assumption. So we have a population mean of $2.32, and here's the given standard deviation. It's 0.17. We know that our sample size is 100, and our sample mean is $2.78. Oh, I did that wrong. Sorry. I think I said 73 earlier. We're going to assume that everything is normally distributed and randomly selected, all that jazz. So we plug in our numbers, right? We know how to do that because we've done it a couple times. So that gives us a standard error of 0.02. Oops, did I go backwards? Yes, I did. So now in order to get my z-score, I need to plug in the information that's necessary with my standard error, and then I need to look at the sample mean and the population mean. Here's my sample mean, population mean, here's my standard deviation. Here we go, we're at 23, a z statistic of 23. So what do we do? Well, in most of those forms, right, even the appendix that you had for the exam, the table only goes to 4.5. So how in the world do we make that go? That means a z of 23 would be really tiny. So that's the probability that's associated with a z is 0.0. So remember again, the point where I'm rejecting or I fail to reject is 0.05. And here I am at 0.0001. Okay. Now the z-test follows a normal distribution like we've talked about. It does not rely on degrees of freedom, which is something a t-test does when we are comparing two groups. So let's talk about that a little bit more. Okay, probability values. That's again your p-value. We have to first set an alpha. I already used that language today. So we set an alpha. What does that look like? Well, that's the level of probability at which we decide. That's the cutoff where we say, okay, if it's that or less, I'm going to reject my null hypothesis. The most common one is 0.05. Occasionally, you could set it for 0.01, and very, very rarely you would set it to 0.001. They are actually kind of random pieces that we've come up together because of confidence levels. That is the reason why we've set up these numbers, right? It's based on that. So why would it be a p-value of 0.05? Why not 0.06? Why not 0.04? Well, it's really just that that's the level of risk we're comfortable taking, and saying a 5% of risk is usually what we do. And it kind of falls in line with our confidence level as well. So 0.05 is what you're going to see most often. Keep that in your noggin. That's what we're going to be using. Okay, so here are the steps. You want to test a hypothesis. How do you do it? First, you have to make some assumptions. Hopefully they are grounded in research literature and you're just not randomly pulling things out of your head, but it could also be that, right? When you first start doing research, you may not know or have a whole lot of back knowledge on a specific topic. So you're going to start by making some assumptions. You're going to state your research and your null hypothesis and select an alpha level. Then you're going to select a sampling distribution and specify a specific test, a test statistics. Then you're going to compute that test statistics and you're going to make a decision and then interpret your results. Those are the 5 steps you take every single time. And it needs to be in that order. And I tell my research students this all the time. You cannot go, oh, I wonder what's the relationship between this, and not really have a well-formulated hypothesis, then do the data, and then create a hypothesis and then say, oh, I reject the null, right? That is very bad research science, because that's letting the data speak and then you saying, oh yeah, that's what I thought. That's kind of the annoying person who's always like, oh, I knew it was going to be like that. And you're like, well, have you guys ever had that? Like, well, I knew we were going the right way, but I just didn't tell you. And then you're like 15 minutes down the road going there. I'm like, why didn't you just tell us, right? Why didn't you say from the beginning, this is a wrong turn, don't do it? The whole hindsight piece, that's super annoying and incorrect, right? So if you need to first, at the beginning, state what you suspect the relationship will be, and hopefully that's grounded in research, then test it out, and then interpret the results to see if you reject your null hypothesis or if you fail to reject it. Okay, I'm going to break down these into each little tiny chunks. So first, making assumptions. So statistical hypothesis testing involves, again, making those assumptions about the level of measurement of the variable, the way you're going to sample it, the shape of the distribution, and then how large of a sample size you're going to use. You need to always be looking for a random sample. We don't want to be stacking the deck. So for instance, with this specific one, you want to make sure that when we're using price, that you're using interval ratio level. And with this specific example, we can assume that because of central limit theorem, because the sample is larger than 50, we'll assume that it's a normal population. Then you state your research and null hypothesis, and you state your alpha. So again, this is my alternate hypothesis that the mean of gas in California is greater than the national average at $2.32. My null hypothesis is that it is the same as the national average at $2.32. And I select an alpha of 0.05. And at that point, I say anything smaller than 0.05, I will then reject the null hypothesis. We following so far? Is this all making sense?
Yes.
Okay. Stop me at any point if something is like you're unclear.
I'm just writing stuff down.
Oh yeah, no, it's fine. Anybody, again, anyone can stop at any moment. Happy to help. Okay. Then you need to select the sampling distribution and specify the test statistics. So how are you going to go about sampling them, and what is the test statistic that you're using? It's usually going to be a normal distribution, and usually we're going to use a z-statistic. You then compute it. In our example, z-statistic was 23. Then we make a decision as to whether we reject or we fail to reject based on the score that we got and the probability level that it fell into. Based on that, my concluding statement would be that we reject the null hypothesis, and California gas prices are significantly higher than the national average. This is key also. Circle, asterisk, put it in bold. That is the language we use. We use the word significantly. Because we are using statistical significance, using the word significantly here informs your reader right away, without having read any of the stats, that the standard error or the probability that it was due to chance is less than your alpha. Right away, they know that it was a significant finding. So whatever your results would be, that there's a significant difference, or it's significantly lower, significantly higher, whatever the wording is, you keep significant in there, okay? All right. Want to be mindful of time. Let's go another 15, then we'll take a short break. This is kind of a longer lecture. Okay, so hypothesis testing and the risk of making errors, okay? This is very, very salient to many, many domains, okay? A type 1 error is the probability associated with rejecting a null hypothesis when it is true, okay? So it's a false positive, it's a false alarm, okay? It's saying, I told you you had cancer. Just kidding, you don't, right? You don't. So I thought there was a significant difference and I rejected the null. Turns out, nope, you're all good, right? Okay.
Would you say
So,
that type 1, sorry to interrupt, but
no,
would
it's
you
good.
say type 1 error is the most common error? Or is there not a really like most common? It's just like
There's not, yeah, there's not more common. So I take that back. So again, I don't want to dive into thoughts on COVID, but this is very relatable to COVID. There are many tests that are going to be created that are going to say, hey, I am very uncomfortable with any level of type 2 error where someone has a false negative. I'm very uncomfortable with that. I would rather somebody be told, hey, you have COVID and you don't, than the other way around. Hey, you're fine. Go meet everybody in the world and spread your germs. And then, oh, just kidding. You actually had it. And now let's contact trace, right? So there are going to be some tests that are going to work to reduce type 2 error. And we're going to talk about the wording with that. So they're going to be more specific, less sensitive.
Okay.
Or more sensitive, less specific. Pregnancy tests would be another one. Pregnancy tests are probably more likely to throw out a false negative than a false positive, okay? You're more likely to go, oh my gosh, I think I'm pregnant, right? Right, like that's, again, we're gonna talk about this in a couple slides, so we'll go into that. But it's, again, based on the specific test you're doing, you may have a particular, your threshold of error may change, okay? So type 1 error, so again, it's a false positive. Type 2 error, it's the probability associated with failing to reject a null hypothesis when in fact it is false. It's a failure to detect a difference, and it is a false negative, okay? It's important to note type 1 and type 2 errors are inversely related, right? The more sensitive a test is, the less specific it is. Reverse that as well. When you reduce a type 1 error, you increase a type 2 error. When you reduce the rates of false positive, you increase the rates of false negatives, okay? It's really an inverse relationship. Okay. So here's the decision that you make. You either rejected the null hypothesis or you did not reject it. And this is the reality. Actually, the null was true or the null was false. So if you rejected it, but the null is true, you made a type 1 error. If the null is false and you did not reject it, you made a type 2 error. All right. If you did not reject the null and the null is true, that's a correct decision. Yay. If you rejected the null and the null was false, again, correct decision. So this is how we go about figuring out type 1 and type 2 errors. Questions about that? These are important because, again, if I am reading my statistics, or if I did something wrong with my math that leads me to a probability that is less than my alpha that I stated, then I will likely reject the null hypothesis because that's what I've been, right? That's what I'm teaching you to do. But if your math was incorrect, you reject the null when in fact it was true. That's called the type 1 error. So, all right. T-test. Let's stop here actually, because I'm about to switch in a totally different direction. Can we just take like a 6-minute break? Can we handle that?
Yeah.
Okay. Come back on. I'm going to start converting this for our YouTube page. 6 minutes. Let's come right back. Okay, guys.
See you soon.